lecture 3 in a introductory course to electricity and magnetism. And the subject of this lecture is electric force vectors and the Coulomb interaction. This is the first time in this in this series of lectures, which we're not very far into, that I'm going to introduce a quantitative topic, and it's a vector-based quantitative topic. So the learning objectives are quantitative. You're going to learn to calculate force vectors in electrostatic interactions. That just means electric charge repulsion or attraction force vectors. And you're as a sort of sub-objective, you must be able to do this in order to successfully do sort of the overarching thing. So I'm also going to describe how to construct what's referred to as a unit vector. All right, so this lecture is basically got two big ideas in it. One of the ideas is this formula right here that I hand drew in this lecture document. This is Coulombs Law right here. It's a quantitative force law. That is, it's an equation, and you can put numbers and also vector quantities in these places. So this equation gives you a force vector. It's a vector equation. So I wrote out how you would read this formula here, this equation. I think it's valuable to be able to sort of say it out loud, like literally. So you could read this, and it is a reading of the formula itself. The other big topic, besides Coulomb's law, is, like I said up here, it's a sort of sub-objective that's required to be able to do the big objective. It's the idea of the unit vector and how to actually make one. That is, you're going to write down the appropriate unit vector expression such that you can put it right here in the formula. So the thing that I'm circling with a little mouse pointer is the unit vector. And so there are some instructions on how to construct such a thing, and here it is. So this is the thing you want to build, and the way that you build it is you do the following thing. You take a vector and you divide it by its length. That's simply it there, and that's the unit vector. So I'll show you an example of discovering a unit vector in this course, or in this lecture today. I want to add a comment here. So I'll add it down, after this. The comment is this. I tend to do vector mathematics, with the unit vector formalism. And what I mean by that is the unit vectors I, J, and K represent unit vectors in the X, Y, and Z directions respectively. Yeah, so this is how I'm going to do it. The other way is to use magnitude and angle to represent vectors. And honestly, it is a equivalent way to do stuff. But I find the I hat, J hat, K hat formalism much more transparent, honestly. You might have to review vectors. So if you find yourself needing to review vectors, you really ought to do it. In fact, actually, you might find that doing this physics is going to actually teach you more about the vectors you're using. You're going to become more comfortable with this kind of mathematics or this kind of structuralization of the physical idea. And Coulombs Law looks like this. This is often what you see in a book. See in a book, you're going to see an expression that looks like this. It's going to be sort of bare bones. F equals 1 over 4 pi times epsilon sub 0, or epsilon naught. I like to use the word naught. It's sort of an old word. So 1 over 4 pi epsilon naught times the charge of one of the objects times the charge of the other object. There's never 3 objects represented up in here, it's just 2. And then you divide by a distance squared. So this is the sort of what you would see in a book. So this represents an electric force, and where is the vectorness? So the idea is force is a vector. So we really want to be able to get a vector. And the vectorness is actually really easy to write down in a physical way, but it doesn't give you sort of an automatic mathematics to calculate the vectorness. But the vectorness comes from opposites attract and likes repel. So this is where the vectorness is. Up here, this is simply going to give you the magnitude of the forces. So this thing, if you'd like, you could say it's what you would get if you ask what is the magnitude of the force vector, or of a force vector between the, or from the interaction between charge A and charge B, which are a distance r apart. So here's an example. Let's say I've got a charge, and let's say it's a positive charge. So I'm going to say, how about 2 microcoulombs, like this. And here is another charge. I'll make it negative. So these are opposite charges, and the negative charge is up here, and let's make it charge negative 3 microcoulombs, like this. So micro, remember, is 10 to the minus 6. So this is also 2 times 10 to the minus 6 Coulomb, for example. And let's say that these 2 point charges, so these are point charges, they are separated by a distance, r. R is the distance between the centers of the point charges, not the near edges and not the far edges either. It's really just about the centers, just like in gravity. Let's say that r is 5 centimeters. So I've got some data. The distance of separation, 5 centimeters. I've got a charge up here. It refers to charge A and charge B. It doesn't really matter who is A and who's B, so I'm going to upset the balance a little bit. I'm going to call this A and this one B. So the charge of A is 3 microcoulombs, but it is negative. And the charge of object B equals, oh, you know, I just realized that I made a mistake. So I'm sorry to pause. I'm going to go back up in here, and I'm going to quickly do something.
So 1 over 4 pi epsilon naught. I haven't told you what the permittivity of free space is, but that's what this epsilon naught is. All of this stuff here calculates to be a positive number. A distance squared is always positive. But when the signs are opposite, the signs of the electric charges QA and QB, if they are opposite, this will always give a negative number, and magnitudes are never negative. So the way I fixed that, or I fixed this, is I put magnitude bars around the charge product. So, sorry, back down to here. I realized I made that mistake earlier. So QB is 2 microcoulombs, like this, and immediately I can calculate F, right? So F is this 1 over 4 pi epsilon 0, and then I'll be putting in QA as 3 microcoulombs with a minus sign, and I'm going to multiply by the other charge, 2 microcoulombs, and the instruction is to take the magnitude of that, and then I divide by the distance squared, so the distance is 5 centimeters, and I'm going to have to square that. So the number 4, you already know how to use it. The number pi, remember pi is something like 3.14, and then the number epsilon. Epsilon is an experimental quantity. Let me show you what it looks like if you were to look it up on the computer. I think this is instructive.
What I've looked up is I just Googled what's called the permittivity of free space. This is what this epsilon 0 number is. This will be the Wikipedia link. But right here is what Google spat back at us, and instead of calling it the permittivity of free space or epsilon naught, they call it the electric constant. That's just another name for it. We will possibly have reason to talk about the physics of this number, but right now just take it as an experimental quantity that somebody or a bunch of different people measure. And its measured value comes out, you can see it's got quite a lot of significant figures, a 10 to the minus 12, and then a bunch of units. You'll recall the meter, the kilogram, and the second, but this unit I alluded to, I think in the first lecture, it is the amp. It is dimensionally, it's charge per time, but the amp is an SI unit, so it is the Coulomb per second. So let me copy this down into my paper, and then I'm going to mess with the units for a second and show you something cool.
So epsilon naught, right here, I'm copying from the computer, 8.85418.782. Whole bunch of significant figures. They've got 1, 2, 3, 4, 5, 6, 7, 8, 9 sig figs. Multiplied by this factor of 10, which is not significant figures, but it tells me where to put the decimal point. And then I've got some crazy units. Got meters to the minus 3, kilograms to the minus 1, seconds to the 4th, and amperes to the square. So those are the units on this permittivity of free space. All of that goes down in the denominator next to the 4 times pi. So I can take this number, has all those crazy units. I've got units inside the expression as well. Pi does not have units and 4 does not have units, but what's going to happen is I'm calculating a force, and the force unit that I expect to see is the Newton. And if I look in this units list here, I do not see the Newton, right? I don't explicitly see the Newton. And I don't see the Newton anywhere here. So I wonder, how am I going to get newtons on the left-hand side if nothing on the right-hand side has units of newtons? So let me show you where the Newton is. So let me rewrite, or actually let me just take the units of epsilon 0. So the units of epsilon 0 are 1 over meters cubed, 1 over the kilogram, seconds to the fourth, and the amp squared, right? These are just the units. The amp is a coulomb per second, 1 over a meter cubed, 1 over kilograms, seconds to the fourth, and coulombs squared per second squared. That's what happens to the amp, right? I get 2 factors of Coulomb, 2 factors of the second. And if you go through, you notice that I'm just have a string of equals, so I'm just going to mess around. So I've got seconds to the fourth over seconds squared. I'm going to cancel 2 of the seconds against 2 of the 4 factors of the second above. So I'll be left with second squared, Coulomb squared, divided by meters cubed, kilograms. So as an interlude, remember actually drop the vector symbol, but F net equals MA, and in SI units land, this is the Newton, right? Forces in newtons. The SI unit of mass is the kilogram, and the SI unit of acceleration is the meter per second squared. So what this means is that the Newton is the kilogram meter per second squared. So I'm going to find this thing up in here. Check it out. If I separate off 2 of the factors of the meter and separate off the Coulomb square, because charge is nowhere in this expression for the Newton, so I'll just separate it off, and what's left over is seconds squared over, remember I have meters cubed, but I only took away 2 of them, or I put 2 to the side, so I've got meters, kilograms there. So here is where the Newton is. And so what this looks like, let me close this off in a box. So this set of units is actually the following thing: Coulomb squared per meter squared 1 over the Newton. So let's calculate 1 over 4 pi epsilon naught, knowing that epsilon naught's units can also be written in this interesting way. So here's epsilon naught. So I've got 1 over 4, and then since I have, here is epsilon naught up here, I had 9 significant figures. It turns out that pi has a lot of significant figures too. It's got, honestly, it's got an infinite number of significant figures, and we often represent pi with an abbreviated set, right? An abbreviation or a truncation, or actually not a truncation, a rounding. So I'll write pi as 3.141592654. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And actually, so if I want 9 sig figs, this actually was a roundup of a 3. You can go look up a bunch of digits of pi if you want. So I'm going to scrub that off. And now I've got 9 significant figures, the first 9 significant figures of pi. So I'll put in 3.141592655. And then, so that's pi. There's a factor of 4. And then the epsilon naught, it's this number, 8.85418782 times 10 to the minus 12. So I've got this little tiny number there. And then I've got these units, which I have re-represented this way. And they're all on the bottom with the epsilon naught, right? So Coulomb squared per meters squared times the Newton. So this is what epsilon naught is. And at this point, I can't do any of this in my head. Well, actually, a couple things I can do in my head, actually. This is pretty cool. I'm going to do this in my head. So all of this is in the denominator. When you divide by something really, really small, you get something huge. So it's 10 to the 12, positive 12 on the top. So it'll be 10 to the 12th. And then when you move things on the bottom to the top, you flip them over. So this is the meter squared newtons per Coulomb squared, like this. So that's all on the top. And now I've got to multiply by 1 over 4 times pi times this 9 significant figure number. And people can't often do that in their head, including me. So I'm going to take 4 multiplied by 3.14159265 and multiply times 8.854187882. I think I did that right. And it's equal to this number, but everything is on the bottom, so I'm going to ask my calculator to flip it over. So x to the minus 1 flipped over is this 0.008987552, which is only 1, 2, 3, 4, 5, 6, 7 significant figures. The calculator wouldn't calculate for me 9. So this is 0.008987552. And so let's finish this up. So 1 over 4 pi epsilon 0 out to 1, 2, 3, 4, 5, 6, 7 significant figures. I started with more, but I'm going to take this and run with it. Because you notice back in this problem, I only had 1 significant figure for the charge and 1 significant figure for the distances. These physical sort of experimental quantities, maybe you'll have 3 or 4 significant figures. You won't have, yeah, you won't even have 7. So anyhow, I've got this. So I've got 10 to the 12, but I can move this decimal point 1, 2, 3 spaces over. So this is 8.98, 8.987552, and the units are, I'm going to turn it around a little bit. It's newtons meters squared per Coulomb squared. And if you were to remember this or write it down somewhere and use it, this is a useful quantity. You'll never have to recalculate 1 over 4 pi epsilon naught. You just remember this. And often, actually, it depends on what physics book you look at, but this is often encapsulated into a constant called lower k, sometimes referred to as Coulomb's constant for the electric force. Yeah, here it is. All right, so let's move on. So I've got this epsilon naught now, or at least 1 over 4 pi epsilon naught. It's this. Oh, you know what I forgot? I'm so sorry, I forgot something. So remember I moved the decimal 1, 2, 3 here, which means I had to take it from there. And so this is times 10 to the 9th. I went 1, 2, 3, or 12, 11, 10, 9, right? So take 3 steps down from 12 because I moved over by 3 there. So it's 10 to the 9th. Very big. Sorry about that. So abbreviated, it's about 9 times 10 to the 9th. Can you see how sort of efficient this way of remembering it is? 9 times 10 to the 9th newtons meters squared per Coulomb squared. All right, without further ado, let's finish this original problem. So the original problem has these 2 charges separated by 5 centimeters, and each of these things has a charge. So I can go and I can finally calculate this. So let's do that. Let's see what kind of number we get. So the force will be, so I'm going to do some rough stuff, so rough calculation. 1 over 4 pi epsilon naught is 9 times 10 to the 9th newtons meters squared per Coulomb squared. So that is using this formula here. So 1 over 4 pi epsilon naught, but epsilon naught has been rewritten as about 9 times 10 to the ninth with those units. So I'm gonna continue to fill out this expression to calculate a force, and it is, I'll cut to the chase. It's 3 times 2 is 6, but it's microcoulombs squared. Be really careful, because remember, I've got 2 factors of the microcoulomb here, 2 factors of the microcoulomb, and then I'm going to divide by 5 centimeters quantity, right? The radius is, or the distance is 5 centimeters, and I have to square all the details about the distance. So square the 5, square the centimeters. So I'll be dividing by 25 centimeters, and the unit, the centimeter, is squared. Now the reason I'm making the point of putting the parentheses around the units is because even the prefactor, the micro above and the centi below, also gets squared. So what does this mean? So this is 9 times 10 to the ninth. It's got newtons, meters squared per coulomb squared. There's a factor of 6. There are 2 factors of micro. So this is 10 to the minus 6, right? That's what micro means. But there are 2 factors of it because I'm squaring it. And then there's the coulomb squared. Can you see the 2? It's a millionth of a millionth. And then I divide by 25 times the centi squared, 10 to the minus 2, 10 to the minus 2, right? Centi means 1/100th. So these are 1/100th, 1/100th. There are 2 of them because the square. And then meters squared. And so if I continue, I've got 9 times 6, 9 times 5 is 45, 54. So 54 over 25, right? 54 over 25. Can you see what happens? The Coulomb squared and the Coulomb squared, they cancel on each other, and the meter squared and the meter squared divide each other out to 1, and the only unit left over is the Newton. But I've got 10 to the ninth, I've got 10 to the minus 12th, and then I've got 10 to the minus 4 on the bottom becomes 10 to the positive 4 on the top. So this is 10 to the 13th minus 12, and the units are newtons. So this is 54 over 25, 10 to the 13 minus 12. That's how exponents work, units. Units of newtons, and then 54 over 25, whatever it is, it's about 2, a little bit bigger than 2, times 10 to the first power times the Newton. So a little bit, it's roughly 20 newtons. So this is quite big. I have a picture that here is a charge B, and here is another charge A. And they have an interaction force of about 20 newtons between them. So opposites attract. So these 2 charges are attracted to each other. You'll recall that this was -3 microcoulombs, and this was +2 microcoulombs. And you notice that this is the larger charge, and this was the smaller charge. So regardless of who's larger and who's smaller, there was a force that we calculated as about 20 newtons. But we didn't calculate a large force and a small force because there isn't a large or small force. According to Newton's third law, you get equal in magnitude, just opposite in direction. Right? This is Newton's third law about interaction forces. So I have this interaction. It's an attraction between these 2 charges. The attraction forces are 20 newtons in strength. So that means that A is pulled at B at 20 newtons, and B is pulled exactly at A with exactly the same strength of force, 20 newtons each, towards each other, right? That's what attraction means. So we would say that this force vector right here, this force vector is the force that acts on B by A. And this force vector here is the force that acts on A. Can you see that it looks like it's tugging on A? And it's because of B. B pulls on A. This force is A pulling on B. This is what Newton's third law is describing. All right. So continuing on, I'd like to make this a little bit more precise. I'm going to use the very same data, the charge, and also the separation distance of 5 centimeters of separation from earlier. But I'm going to be really precise about where the two charges are in a coordinate system so that I can do some vector stuff. Let's put these charges on, or the charges from the earlier problem, let's put them on a coordinate system. So for this first example, we'll just keep it two-dimensional. So we'll have an x direction that we move along with this unit vector I hat, and a y direction that we use j hat to go up and down. All right, and then for fun, I'm going to put the little positive charge here and the little negative charge over here. And you remember that they are 5 centimeters apart. And I'm going to put these, so you notice that the positive charge is not at the origin. Maybe I'll put this one at 2 centimeters. I'll put this positive charge at 2 centimeters in the y. So it's got a coordinate, 2 centimeters comma 2 centimeters. So it turns out that if I was to put the negative charge at 6 centimeters over, so that's 4 centimeters in this direction, and at 5 centimeters here, so that's 3 centimeters in the y direction. So it'll be 3 centimeters, 4 centimeters. That turns out to give me a hypotenuse of 5 centimeters. So this matches our earlier problem. Our earlier problem is here. The 2 microcoulomb charge is down on the left. The negative 3 microcoulomb charge is up on the right. They are separated by 5 centimeters because if you use the Pythagorean theorem, you'll see that the separation is 5 centimeters. So so these charges are known as B and A. And I'd like to point out some stuff. We already know, so they are 5 centimeters apart from there to there. And I'm going to draw a little bit of a triangle. So along this side, this is 4 centimeters. And along this side is 3 centimeters, right? Also some information that I have that B is attracted to A with a 20 Newton force, and A is attracted to B also with a 20 Newton force, right? We figured a lot of this stuff out earlier. So let's explore a bit. I'm just going to do some stuff. If I was to build the vector that points me from A to B, so this is the vector that points from A to B. the way I build this, so A is over here and B is over there. So the vector that takes me from A to B is going to look like this, right? And it's got to take me from this location all the way over to that location. So that is, it needs to take me backwards in the x direction. So minus 4 centimeters in the x direction. So take me back in the x, but then back in the y. So I have built myself this vector in this unit vector notation. I'm going to clean it up a little bit and say this is minus 4 I hat minus 3 j hat quantity in centimeters. So there's the unit of the centimeters, right? It's a common factor if you look. So it's got two terms, and each term has a factor, one factor of centimeters, so I can divide out from all the factors and put it on as a common factor. So the unit is a common factor in this case. What about the vector that points from B to A? Do you see this? So the order of the indices here, the order of the labels, tells me which way. So the vector that points me from B to A is just the opposite of that vector. It's going to be the vector that does this instead. The tail sits at B, and it points up to A, right, to the head. So if you look at these two vectors, right, this and this have the same magnitude, both 5 centimeters, but they have opposite directions. So opposite is pretty easy, 4I hat plus 3j hat. Opposite just means go and change the sign to the opposite sign on all the directions. And this is also centimeters, right? So I drew these vectors. No reason yet, just because, honestly. But you'll see that they'll become useful in a minute. Let's define slash construct or build the unit vectors. So the unit vector r hat sub ab, let's make the unit vector for the vector rab. So little hat, this is the r hat. It's equal to the vector from a to b divided by the length of the vector from a to b. Like, that's how you do this. This is the construction. So you can just do follow the formula and you'll get the result, the thing that you want. So here's the unit vector. So the vector RAB is this thing right here. It's minus 4 I hat minus 3 j hat all times the centimeter. And then I'm going to divide by the size of the vector AB, right? The size always comes with a plus sign. And the size of the vector is 5 centimeters. You can use the Pythagorean theorem to show you, right? 3 squared plus 4 squared is the same thing as 5 squared. So I'm going to put 5 centimeters on the bottom because the length is 5 centimeters. The length is not just 5. The length is 5 centimeters. So what you'll notice is the units go away, which is always going to happen because you're always going to take the units of the vector, and the units of the length of the vector are always going to be the same. So they will always divide out, and the unit vector will never have units. So this is minus 4 over 5 I hat minus 3 over 5 j hat. And the unit vector from B to A, I bet you can show it to yourself, but it's going to be the opposite of the vector, unit vector from A to B. It's the opposite of the unit vector from A to B. This is just guaranteed because it just points, instead of from A over to B, it points from B back to A. So it's just in the reverse direction. So it's equal to, I'll just switch the sign of everything, right? That's what multiplying by minus 1 on everything means. So it's positive 4/5 I hat plus positive 3/5 j hat. So this is what the unit vector from B to A looks like. All right. So these unit vectors always have length 1. That's what unit means. It means length 1. There are no physical dimensions or units. Strangely, we use the word units. So you notice the centimeters canceled. The units went away. There aren't any dimensions or units left over on a unit vector. All right, so the reason that I wanted to show you these things, I was able to make vectors. This is the vector that points from object A all the way to B. Here it is. Here's the vector that points in the opposite direction, from B all the way over to A. Here it is. These things right here are so-called unit vectors. They don't have length that's interesting, only direction. So the only thing interesting is direction. And sometimes a unit vector is referred to as pure direction because you are guaranteed that there is no length information, because every unit vector has length 1, so there is no length information. It's just direction information. Okay, so the reason I bring this up is because of the expression that I wrote in the lecture notes. It says that the force on B, right, charge B by charge A equals 1 over 4 pi epsilon 0. It's the charge of A times the charge of B divided by the distance between A and B squared, multiplied by the unit vector that points from A to B. So you can kind of see the utility of me trying to understand how to create these vectors. Because in order to calculate this vector, I need to be able to create that vector and understand or create the vector RAB so that I can describe the size of the separation vector. Right, so that's the reason for me having done this. So not just because, it's because I need to be able to create the things. They're not always given to you. You have to sort of build up these quantities yourself or construct the quantities yourself. This is one of your learning objectives in this video. All right, so let's follow this instruction and calculate some force vectors. In particular, why don't we first try to calculate this vector? Let's see. I'm gonna throw you for a loop. I'm going to calculate this one. Let's do this. All right, so there's the 20 newtons. So what we want, right, what this means is we want to know what is the force vector on charge A, right? This is the force that acts upon A, backwards to what I just said down here, kind of. But anyways, this is the force on A by B. All right, so we want to calculate what is the force on charge A by charge B. Well, let's follow the formula, and you'll notice that I'm about to do something funny. Do you see that the first letter in the original definition is a B, lowercase b? It now is a capital A. And the second letter is a lowercase a, but it's now called a capital B. So what I need to do is I need to go through this formula and switch lowercase a to capital B and lowercase b to capital A. So this is 1 over 4 pi epsilon naught Q capital B Q capital A divided by R sub capital B capital A and then multiplied by the unit vector from capital B to capital A. So, right, I had to switch A and B everywhere and capitalize. Cool. So let's go fill this in. So 1 over 4 pi epsilon naught times QB times QA over this 5 centimeters squared, I actually already calculated what this is. It's going to be 20 newtons, right? That's what we arrived at, is this 20 newton number. But I'd like you to remember something really quick. In particular, when I calculated for 20 newtons, I had this absolute value happening to this minus sign. And in this formula that I'm calculating, there is no absolute magnitude bar. So I need to keep the minus sign. This minus sign is really important. It's just what comes from the fact that these two charges are opposite. So I get the minus sign. So let me, so this minus sign is from opposite charges. So everything about negative 20 newtons comes from everything in this red bracket. Right? The charge B was positive, this charge was negative, so overall this product is negative, and everything else is positive, so I end up with a single minus sign. Okay? So everything in the red square bracket is negative 20 newtons, but I need to multiply by r hat from B over to A. So r hat from B over to A, so this is minus 20 newtons, and then r hat from B over to A, I calculated it earlier. Here it is, r hat from B over to A is positive 4/5 I hat plus positive 3/5 j hat. So I'm just going to take this and put it right here. So this is 4 over 5 I hat plus 3 over 5 j hat, like that. So this is my expression for the force that acts on capital A by capital B. But let me do a little bit of work so we can kind of see what we're looking at. It's sort of tough with some fractions around. Luckily, 5 divides into 20 really nicely, and then I can multiply by 4 with in my head. But 20 divided by 5, right, is 4, and then 4 times 4 is 16. So this is negative 16 newtons I hat, and then 20 divided by 5 is still 4. 4 times 3 is 12. So this is minus 12 newtons j hat, like that. So this is my force vector. This is the force on charge A by charge B. So let's see if this makes sense. Does this make sense? So for it to make sense, it makes sense if the magnitude of the force on A by B, right, is 20 newtons. Right, because our problem has 20 newton forces involved. So let's see, does this force have a magnitude of 20 newtons? Well, how do I do that? So the force on A by B, so let me show you a trick. The magnitude of any vector is equal to the square root of that vector dot product with itself. Right? You could say that this is the definition of the magnitude. So there's a vector dot product. So this is the dot product. It may require some review from you as a student if you really want to learn this. You can't get away with faking knowing about this. So anyhow, let's check this. So let's check. So I'm not sure it's equal, so I'm going to check, is it equal? So I want to know about the dot product. So I'm going to take this vector and dot it against itself. So I'm going to take the square root of the vector minus 16 newtons I hat minus 12 newtons j hat and dot it against itself, minus 16 newtons I hat minus 12 newtons j hat. And if you remember, I hat dot j hat is equal to j hat dot I hat equal to 0, right? Dot products of perpendicular vectors add up to 0, or are 0. And then I hat dot I hat and j hat dot j hat are equal to 1. So if you go through and you FOIL out this dot product, you'll get that this is the square root of 400 newtons squared. So you'll do 16 times 16 and then 12 times 12. So 16 times 16 plus 12 times 12 ends up being 400. And then everywhere there is newtons showing up twice, and the dot product's like a product with the units. So it's newtons times newtons. So you're always going to have newtons squared on all your terms. So when you add them up, you get newtons squared. And this is 20 newtons. Be careful. There, in algebra, sometimes a plus minus shows up, but the plus minus does not show up. This is purely a positive number, right, when you ask for the magnitude of a vector. So it turns out this has the right magnitude. But also, this makes sense also not just because of the magnitude, but is it the correct direction? So this is negative in the x, and it's also negative in the y. So at least it looks like it's the right direction, because the force on A by B needs to point negatively in the x and also negatively in the y, right? It points towards the left and downwards. So it sort of seems like the right direction. So what you need to do, short answer is yes,